Welcome to Math 31. This is a lesson on sketching trig functions. Doesn't introduce an awful lot of new concepts, but we do take the graphing things that we've done before and then apply them to trig functions. So to start it off, take a look at a function like this. F of x is equal to 2 cos x plus x, and in a pretty conventional domain between 0 and 2 pi. So just get basically what probably is one full cycle, although we shall see. Now the method is the same as always. We would want to get note the domain if there's any issue with a domain, but the domain is given, and because it's a cosine function and a linear function, there's going to be no gaps in it, so we know it's continuous in that, so we don't have to do any exploration. If you wanted to, you could note things like symmetries. I'm going to play this one a little bit looser because it's not that big of a deal, because we're graphing it from 0 to 2 pi. A symmetry about the y-axis isn't going to help us too much, so we need to be aware of that there's not a lot of point with that. And the same thing about it being symmetric with respect to the origin. Not going to help us too much because we're stuck between 0 and 2 pi. So what goes on to the left of 0 really isn't an issue for us. Asymptotes would matter, but we don't have to worry about asymptotes either, because this vertical asymptotes at least, because this thing is fully continuous between 0 and 2 pi. So we can pretty much go on to things like the intercepts and then get on to the first and second derivative analysis. So let's see what we can do for those intercepts. So when we get the y-intercept, we set x equal to 0. So we get y is equal to 2 cosine of 0 plus 0. Now the cosine of 0 is 1, so this is 2 times 1 plus 0, so y is equal to 2. Now the issue with the x-intercept, now this is a problem, because if we were to set y to 0 and solve this, it would be very difficult to solve. So what I'm going to do is remind everybody for these trig ones is that don't bother. Now you can use your calculator, but it is a really problematic equation. And in fact, in this case, turns out there are no x-intercepts, but you'd have to be solving 0 is equal to 2 cos x plus x. So it's a combination linear and trigonometric function. It'd be awfully hard to get that x isolated and solve for, so I'm going to not bother. Then we go on and we try to work these ones out for the first and second derivative analysis. So first derivative analysis. F prime at x is equal to negative 2 sine x plus 1. So we get the critical numbers. So f prime at x is equal to 0. I'm not worried about where it doesn't exist, because this thing is continuous in that interval. You get negative 2 sine x plus 1. So 2 sine x is equal to 1. So sine x is equal to 1/2. Now this is going to put us squarely into quadrants 1 and 2. And the reference angle that we would get for sines equal to 1/2 is pi over 6 in quadrant 1 and quadrant 2. So in other words, the two angles are going to be pi over 6 in one and 5 pi over 6 in the other. Now we do the interval analysis. I'm going to get a little more space to work on. And we set it up the same way we do everything else. So I'm going to have to freehand this one in. But the only factor we have is negative 2 sine x plus 1. You could reverse that if you wanted. And then the f prime at x could go down below. Now we are aware that the two critical numbers are pi over 6 and then 5 pi over 6. So I'm not perfectly on center with this one, but that's okay. Gives us enough space to work it out. Now, the way you have to deal with these is you have to plug in values in those intervals, and it's not quite as easy with just a polynomial term. So you got to say, pick an x value that's less than pi over 6. Like I would try x equals 0, and then go negative 2 sine of 0 plus 1. Well, the sine of 0 is 0, so this is equal to 1. So it's positive in this interval, and it won't change between at least all the way down to I picked 0. In fact, I should be a little bit careful with this. I did pick 0, but really we are going only down to 0 with this one. So you might not feel comfortable doing that. Now, in fact, because it's not going to change, that was a safe pick. But it probably would have been technically more accurate to pick something like pi over 12 or whatever between 0 and pi over 6. So I kind of cheated a bit. A safe cheat, but it was still, you know, a cheat nevertheless. Now for the next interval between pi over 6 and 5 pi over 6, be careful with this one. I'm going to pick pi over 2. Now that is, nobody can question me on that one because that's between those two and it is not a, and it is within the domain. What I'm trying to do is pick quadrantals, so easy ones to deal with. And I get negative 2, the sine of pi over 2 is 1. So this is negative 2 plus 1 is negative 1. So we're negative in this interval. And then you pick a one that's greater than 5 pi over 6. Now, if you did pick 2 pi, for example, you'd be okay with it. But even, and that is within the interval, I mean, or in the domain. I think it is. Or are we actually inclusive to that? We're not. So 2 pi technically is not. So to play it real safe, why not pick something like pi, which is larger. And then we do that negative 2 times the sine of pi plus 1. It really doesn't matter. Some people just pick a number and drive it through their calculator, making sure they're in rad mode, and they just see positive or negative. This is negative 2 times 0 plus 1, so that's equal to 1. So that's positive right there. So we're going up, we're going down, we're going up. And then we've got the intervals indicated where it's increasing or decreasing. And then we can see that there's a local max at x equal pi over 6. And when we plug that in, we try to find f at pi over 6 into the original, of course. We'll get 2 times the cosine of pi over 6 plus the pi over 6. And that would give us 2 times root 3 over 2 plus pi over 6. And the 2's cancel, so we get root 3 plus pi over 6. So therefore, pi over 6 is the x-coordinate. Root 3 plus pi over 6 is the y-coordinate. So I'm going to decimalize that just to make my life a little bit easier. So let's take the square root of 3 plus pi divided by 6. And it's about 2.3. So this will help us when we do choose to graph this one. And then as you move on, you're going to see that you have a local min. At x equal 5 pi over 6. Now everything works out pretty much the same with this question, when you do plug it in, there's one slight difference, and that would be 2 times the cos of 5 pi over 6. That slight difference is plus 5 pi over 6, is that the cosine of 5 pi over 6 is negative root 3 over 2. So the 2's cancel, so negative root 3 plus 5 pi over 6. And that's your y coordinate when x is 5 pi over 6. And that is a min. Now when you decimalize this one, we can get a better idea of where we're at. So that's about 0.9. So I'm just trying to get a rough look at where they're at. Now that takes care of our first derivative analysis, but we should really find out do the second derivative analysis as well. So our first derivative, according to what we had worked out, is equal to negative 2 sine x plus 1. So our second derivative, so all you're doing is going back and forth between cos and sine. This becomes negative 2 cos x. So it's actually simpler. We do lose that constant term. And we set up the analysis after we get the potential points of inflection. But when we do set this second derivative equal to 0, 0 is equal to negative 2 cos x. So cos x is equal to 0. So where is cos x equal to 0? Well, it's equal to 0 at pi over 2 and 3 pi over 2. So with those two numbers, we can set up our analysis, freehanding this again. And same interval. Here's pi over 2. I'll go pi over 2 right there. And let's move 3 pi over 2 over there. And it's simply negative 2 cos x. And we just see where it's positive and where it's negative. And there's our second derivative. And this will give us our points of inflection. So once again, pick numbers, the easiest numbers you can get. Now, in a case like this, you could certainly pick 0 again. But if you did try x is equal to, just to keep things more interesting, I'm going to go pi over 3, which is to the left of pi over 2. And then negative 2 cos pi over 3. Well, cos of pi over 3 is 1/2 times negative 2, so that's negative 1. It is negative in this interval. And then when you get to pi over 2 and then 3 pi over 2, try x is equal to pi. A nice easy quadrantal between them. Negative 2 cos of pi is negative 2 times negative 1 is positive 2. So we're positive there. Move into quadrant 4. And, you know, if you did 2 pi, because that's not a natural endpoint, you'd be safe. But I'll play it strictly by the book. I'm going to pick, how about 5 pi over 3, because I know that's an easy number to work out. So I'll go negative 2 cosine of 5 pi over 3. That's going to be positive 1/2, and then negative 2 times that is negative 1. So we're negative there. So we're negative, we're positive, we're negative. If it's negative, it's concave down, then concave up, and then concave down again. So we have points of inflection at, first off, x is equal to pi over 2. Now when you substitute that pi over 2 in to the original f at pi over 2, it's not going to be perfect, but we go right into the original, giving us 2 cos pi over 2, so 2 cos x plus pi over 2. Now that's going to give you 0, 2 times 0 plus pi over 2. So it means our ordered pair, a little sloppy here, is pi over 2, comma, pi over 2. Now that, if you did decimalize pi over 2 just for the sake of the locating it on a graph, that's about 1.6. So that's where the inflection changes. Okay, so now we should be okay with this. Let's see where the second one takes us. So it's tight for space, but if we do find f at 5 pi over, f at 3 pi over 2, more like it, you'll see that that's going to be 2 times the cos of 3 pi over 2 plus 3 pi over 2. So the cos of 3 pi over 2 is also 0, and then we get 3 pi over 2. So that would mean that the point of inflection is 3 pi over 2, comma, 3 pi over 2. And when you decimalize that one, so 3 pi divided by 2, you'll get 4.7. So we can locate that on a graph pretty easily. So now that we have all this, let us graph it. Now, we got our first, our max and min points. I'm just going to take this one back just to remind myself. There's a max at pi over 6, comma, root 3 plus pi over 6. So that's about 2.3. So there's a max at about 2.3. Also be aware that we have a y-intercept of 2. So when we start that graph off. So this is a max. We have a min, if we go back to the second one, at 5 pi over 6, which is right there. And I believe there's about 0.9 or something like that. Yeah. So 5 pi over 6 is about 0.9. So this is where it's turning around again. That's it. Now, in terms of concavity, it's increasing till we get to that value. But the concavity, it's concave down. This is interesting, from 0 to pi over 2. So it's going to have to, I guess that's not that interesting, it's going to have to go down like this. Oh, shit, it's not looking too good. And then at pi over 2 it changes to concave up. And it remains concave up all the way until it gets to 3 pi over 2. So past the turning point. And it's concave up. And it is also increasing. And then at 3 pi over 2 it does shift to concave down. Now 3 pi over 2, I think we got that y value to be about 4.7. So we're up there as a way. So we're up there, and then it shifts over to concave down again. So it's not a beautiful looking graph. It actually ends at 2 pi for our sake. I do conveniently have another graph of it so we can get a look at it, and your calculators would do a fine job of this as well. But points of inflection right there. We've got them labeled earlier, so I'm not going to do anything more with them other than indicate them. And there we have it. Just like old times. So this is a little bit better, but you can see what's going on. It actually rises quite a bit. And there is, if you did go further to the right, you're going to have a max coming at you fairly soon, another max. Now this next one isn't quite as detailed. We want to get the extreme of this, and so we don't need to do the second derivative thing, just do the first derivative. In fact, you don't even have to graph this one. Odd though, because it's been negative pi over 2 to pi over 2, so that will affect our answer. But I'm going to go right to f prime at x, and should be aware here that it's not going to affect our answer, but x cannot be equal to pi over 2 or negative pi over 2. Now that's not within the domain, so we don't have to be too worked up about it. But tan does have an asymptote, so you should always check to see if that's within the given domain, but we're covered. So it's clear sailing. And f prime at x would be equal to 2. minus secant squared x. And now when we get our critical numbers, all we need to do is set this equal to 0. So 0 is equal to 2 minus secant squared x. So secant squared x is equal to 2. Take the square root and you'll get secant x is equal to plus or minus square root 2. And we're solving this trig equation, so we have to put it as cos. Cos x is equal to 1 over plus or minus root 2. And this is going to put you in all quadrants. And our reference angle, where cos is equal to 1 over root 2, is pi over 4. And we take a look at our 4 answers, and x in quadrant 1 is pi over 4. In quadrant 2 is 3 pi over 4. Then in quadrant 3 is 5 pi over 4. And then 7 pi over 4. Now, our domain is simply between negative pi over 2 and pi over 2. So this one we can keep in that form. Now, this really is going to be in quadrant 1 and quadrant 4, because that's all that pi over 2 in both directions is going to give us. So anything that's in quadrant 3 or 2, we have to reject. So this one and this one, in other words. And then this one, 7 pi over 4, has to be written in a negative rotation. So this is actually be negative pi over 4. So we need to be aware of that. These are our 2 values for our critical numbers. So I'm going to bring up, get another screen going, and then let's see what we can do with this one. So for the first derivative analysis, set up our number line. We have negative pi over 4, and we have positive pi over 4. And our first derivative is 2 minus secant squared x. And that's the only factor we have, and that will give us all the information we need about the first derivative. And in fact, this thing is ending at pi over 2 and negative pi over 2. So we don't want to sub in values further over than that. So we picked smaller than negative pi over 2, and you pick something that's going to be a reasonable answer, I guess. That's negative pi. Don't pick negative pi over 6, but how about negative pi over 3, which is to the left of it, negative 60. So what you're going to have to do is go 2 minus secant squared of pi, negative pi over 3. So that's 2 minus 1 over cos of negative pi over 3 squared. Now, easy to do on your calculator. In fact, this time I'm going to do it. So I make sure I'm in my right mode, rads, and I just go 2 minus 1 divided by the cosine negative pi divided by 3, close that bracket, squared. And I get negative 2. So because of that, I know I'm negative. And then pick a number in between for the next interval. So x, say, I think 0 is a good choice. If 2 minus the secant squared of x. So 2 minus 1 over cos of 0 squared is 2 minus 1 over 1 squared. So 2 minus 1 is 1. So you can check that in your calculator if you're not sure. 2 minus 1 divided by cos of 0 squared, do get 1. So we're positive there. And then greater than pi over 4, try x is equal to pi over, I'd say pi over 3. So 2 minus the secant of pi over 3 squared is 2 minus 1 over cos of pi over 3 squared. So 2 minus cos, 2 minus 1 divided by cos pi divided by 3 squared. And I'm also getting negative 2. So I'm negative in this interval. So the first derivative is negative there, positive there, is negative there. So it's decreasing, it's increasing, it's decreasing. So there's a local min at x equal negative pi over 4. And then if you were to find out what f at negative pi over 4 is, you plug it in to the original, which is 2 times negative pi over 4 minus the tan of pi over 4. So this is negative pi over 2 minus, well, tan of pi over 4 is 1. So that's not a very snappy number, but if we plug it into our calculator, negative pi divided by 2 minus 1, we can at least get a decimal value for this. So this is negative pi over 4, comma, I'll write this one out as negative pi over 2 minus 1. And that is about negative, I'm getting negative 2.6. And right above that, I'll go for the local max at x is equal to pi over 4. So f at pi over 4 is equal to 2 times pi over 4 minus the tan. Oops, I think I just made a mistake, didn't I? I plugged in positive pi over 4 for this earlier one. Wait a sec, so that's plus 1. Everything changes. So excuse me for that. Pi divided by 2 plus 1. So make the correction here. So this is negative, I'm just going back to this. I'm getting negative 0.57. Might make a little bit more sense. So be careful with that. That was the original. That's 10 of negative pi over 4. Here this is positive pi over 4. That was close. So here I get pi over 2 minus 1. So our y-coordinate would be that, pi over 2 minus 1. So this is much easier. So pi divided by 2 minus 1. And that will give us positive 0.57. So a little untidy there. Now before we take a look at the graph, I did create a graph for this one. I should bring up something that you're probably wondering out there. For the critical numbers, when we set this equal to 0, you're probably thinking, okay, secant is 1 over cos squared. So the fact is, other critical numbers where f prime at x doesn't exist. Now I didn't bother with it because it wasn't an issue. But you know, you're thinking 2 minus 1 over cos squared x. Where is cos squared x equal to 0? I didn't bother because this is going to be x is equal to pi over 2 and 3 pi over 2. Should have indicated it, but these are outside the domain. So make a note of that. That was my oversight, although I did have it filed away. But it's a good habit to be considering those. So you want to be aware of that. So little details like this that really can be a bit of a problem. So let's take a look at what we have then. We have this local min and we have a local max. And here's our graph. Now this graph also is, I didn't do the symmetries on it, but it is symmetric with respect to the origin, looks like. And pi over 4 is about right there. And this looks pretty good. 0.57 is about where that max is. And then down here, looks like that's where a min is. So I'm happy. Those are the extrema. The graph matches what we should have gotten. So that takes care of that. The next lesson will be on applications. And so it'll be quite a change from this. Thank you for your time.